Okay, so here is another example. Once again, I took it from my book. This is for a rigid body kinematics dynamics example, class 17, and this is example 2. And this is a 4-bar mechanism. Okay, and we have an omega CD of 12 radians per second counterclockwise, and it's accelerating at 25 radians per second counterclockwise. And the dimensions are as provided right here, 600, 400, 350, and there's a difference of 200 right here. And from previous examples, we would have found out the angle here, so we did a position analysis, and then we would have done a velocity analysis and found out the omega AB. So that's going to be which one right here? We find that this one is going this with omega AB. And then we would find omega BC was coming this way, right? So, so now we have these velocities, and now we have to do an acceleration analysis. And what we should do is we should march through the pieces, and I've put them side by side. I think this is missing some arrows right here. So that right there should be the arrow here, and I'll keep color coded right there. Should be the arrow here. And we're going to see there's going to be 2 components of acceleration. And it's going to be nice. One nice feature of this for this part of it right here is that the tangential one is entirely in the y direction, and the normal one is entirely in the x direction. That's kind of it sort of helps us out. Then we could go to, I'll skip over this link, and I'll come up to the link AB, and that because that's another pinned link. And we'll place on, let's see, well, we do know the direction of omega AB, but we don't actually know the direction of alpha AB. So we'll assume that it's in the counterclockwise direction. And notably that these two also has normal and tangential directions. Unfortunately, they're not in the aligned with the x and y axis, but we'll make do anyway. And so we could now go over to link BC, and we could apply what we know about it. We do know the acceleration of, we're going to be able to find the acceleration of C, because this is going to be based on stuff that we were given right here. And so that's the one we're going to use as the reference. And so that's the one where we're going to pin over here. And I think I went ahead and I assumed a clockwise. I have to be careful when you do that, but make sure we make a note of it. We're going to assume a clockwise angular acceleration. So let's see what we do with it. So here's all those diagrams repeated. So we march through. We do the acceleration of point C of the crank, CG. Now that should be CD. I should write all these down. So we find it in the x direction. That's easy enough. That's omega squared times L. And then we find it in the y direction, which is the tangential. And so we have this coming up. And now we come over and we go for the rocker, which is rocker, I should probably say rocker AB. And that's the acceleration of B, and is going to equal the acceleration of B with respect to A, and that's going to have 2 parts to it, the tangential and the normal part. So the normal part, just the magnitude of it. Okay, so we're just going to get the magnitude, and then we could break it up, or we could write down. You see right here, I am writing the magnitude, but I also know the direction based on the angle of this thing. It's going to go up and to the left, and I could get the tangential one, and that one has something that we don't know in it. That has this alpha AB. So we have to keep a track of that. And then for link BC. Where'd you go? Yeah, for link BC, that's the that's the coupler. We could write this equation for this diagram right up here. So this equation corresponds with this diagram, and we could break down what's going on here on the left. Well, we know it's going to be the stuff that we found over here, right? Because so all that stuff gets applied up there. So instead of like breaking it down into x and y completely here, I'll keep it as tangent, but I'll do the y component of the tangent and the y component of the normal. And then I'll write it for this next piece right here in the y direction. And what we're left with, as you'll see right here, we have an unknown. This a, b, this acceleration of b with respect to a in the tangential direction is unknown right here. But then it turns out to be that's the alpha ab from up above, right? That's from like right up in here. And we stuck down right down in here. And we have the cosine of the thing to be able to get the vertical direction. And okay, so from that we're able to find what the angular acceleration is. So that was nice. That was a good thing. And then in the x direction, we apply the same stuff. We're taking down the components of the components, and we know that we have the alpha AB here, but we just found what that was. And from this equation, we're able to figure out what alpha BC is. And so these are the answers right here. Well, I don't know if I asked for alpha BC, but we don't normally, that's the thing that we want to do. And as soon as we have these alphas, we're able to find the acceleration of any given point. So that's the end of the show for this example. Hopefully you're able to walk through it, but more importantly that you'll be able to have a problem and then arrive at the answer. That's more important. Ta-da.